We are continuing in our operations research course, and we're still talking about ways to solve linear programming problems. But there is a certain topic that we want to talk about today, which is the sensitivity analysis. So after you do your solution for your linear programming problem, regardless of the method you used, then usually the analytical people use a sensitivity analysis to see how the changes for certain parameters in the linear programming problem affect their overall solution or for their optimal solution. Okay, what is sensitivity analysis? Sensitivity analysis is concerned with how changes in the linear programming parameter affect the optimal solution. Linear programming parameter means the constraints and means the objective function, as well as we are seeing moving forward. So the motivation for the sensitivity analysis, what make you do that? So usually the coefficients or values in the mathematical formulation, they can give you only an estimate for the solution. So if you need to know how much error you have in your problem and how the sensitive is the solution, and the quality of your numbers need to be assessed with the sensitivity analysis methodology. So as we discussed in the past, we have usually a problem that's a linear programming problem. Then in the first, let's say if you're using simplex method, you have what people call it initial dictionary, or you have your base matrix as we saw previously. Then you go with your optimal dictionary, which means your optimal values. Then you go and you find your optimal solution eventually. Then probably if you don't like your optimal solution for some reason, you could do a modified optimal solution, or you can go back here from problem. Then you have modified your problem, then you have modified your initial dictionary, modified your optimal matrix, then you modify your optimal solution. So the modified problem usually obtained by changing the objective function, or changing right hand side of the constraint, or adding a variable or activity, or adding a constraint. So remember the example we discussed previously, which is about the factory that's making soldiers and trains. So we had this maximization problem with those constraints. We have the finishing constraint, we have the carpentry constraint, and the demand constraint as it was discussed in that problem. Then we assumed x1 as number of soldiers produced per week, x2 number of trains produced per week. Then the optimal solution was z equal 180, x1 equal 20, x2 equal 60, or x and y, whatever you want. Then point B was the optimal point. So this point B was our optimal point by that time. Then we have the finishing constraint having this slope, and we had our demand constraint as x equal 40 having this slope. Then we have the carpentry constraint having the slope equal -1. So sensitivity analysis is done usually by the graphical method. So you have two types of graphical sensitivity analysis. Either you do the graphical sensitivity analysis for the effect of change in the objective function, or the effect of change in the right hand side of the constraints. You have constraint equations, right hand side, as we will discuss briefly later. So starting with the graphical analysis for the change in objective function, let's say we have a C1 to be the contribution to profit by each soldier produced. Then for what value C1 for what value of C1 does the current basis remain optimal? So what we're saying here, what kind of value we can give for C1, either reduction or increasing based on the problem, while still having the optimal solution in place. You can see back here there's a point C. That's our point we're talking about. Then we have C1, which is the C for objective function in this case. So we say if the isoprofit lines are steeper than the finishing constraints, remember this is the finishing constraint and this is the isoprofit line. If this line is steeper than the finishing constraint, then in this case the optimal solution will change from point B to point C. So if it's steeper than the finishing constraint in slope, the isoprofit line will make the optimal solution move from B to C in this case. Then if the slope finishing constraint, in that case, the finishing constraint slope is -2. So if minus C1 over 2 less than -2, or the value of C1 larger than 4, then the current basis is no longer optimal, and point C will be 40 and 20 will be the optimal solution in this case. So that's to keep in mind. In this case, our sensitivity analysis say we are failing. We can't go with changing that parameter with that much value. Otherwise, we will lose our optimal point. We want to keep our optimal point the same while assuming new numbers for the C1 or for the objective function coefficient. So if we want to summarize, all the parameters, if all the parameters remain unchanged, then the current basis remains optimal, where the C1 should be either larger or equal to 2 or less or equal to 4, and the Gaiapeto, which is that example of soldiers and trains, should still manufacture 20 soldiers and 60 trains. Then even to keep in mind, even C1 is between 2 and 4, then the factory will still, the factory overall profit will change, even though if you maintain your optimal point. That's the whole point. Like, you are changing the objective function coefficient, which could be a less cost for the factory, while the profit is changing to the better, let's say. If it's changing to the worse, then we want to avoid it. So that's a sensitivity analysis for the objective function. Moving forward, what if we do the graphical sensitivity analysis for the change in the right hand side of the linear programming solution? Then the graphical analysis can be used to determine either to change the right hand side of the constraint will make your current basis no longer optimal, or will keep it optimal while changing that. So we assume here B1 is the number of available finishing hours. So B1 in the example was 100 hours. So what value of B1 does the current basis remain optimal? How far we can go with B1? How much we can reduce or increase the B1 value, which is the available finishing hours or the working hours. Of course, every factory trying to reduce the working hours spent, which means reduce the money spent on workers. So how much we can cut in working hours while keeping our optimal profit or optimal solution. Then from the coming figure, we will see the change in B1 will shift the finishing constraint parallel to its current position, and the current optimal solution is where the carpentry and finishing constraints are binding. So we can see here, that's point B, that's point C. This is the finishing constraint for B1. B1 equal 100 is right here. For B1 equal 80, it will be this slope. For isoprofit line will be this slope. You have point B here and point C here. So what we said in the previous slide, we said the current optimal solution is at point B, and that's where the cross section of carpentry and finishing constraint, which is true. Then the optimal solution still occur where the finishing and carpentry constraints intersect, even if we change the B1 value. So that's a good thing. So as long as the point where the finishing and carpentry constraints are binding remains feasible, then the optimal solution will still occur in the finishing and carpentry constraint intersect, as we can see here. So that's the finishing constraint, and this is the finishing constraint as well, and this is a finishing constraint, as well as both are cross-sectioning. Then we can always still have an optimal solution. So it's good to know, especially for managers who are dipped into operations research in their work analysis. They determine how a change in a constraint for the right hand side of linear programming optimal Z value. While keeping that in mind, you define something called the shadow price. Shadow price is defined as, for the ith constraint of a linear programming problem, it is the amount by which the optimal z value is improved, which is increased in a maximization problem and decreased in a minimization problem, if the right hand side of the ith constraint is increased by 1. So this definition apply only if the change of the right hand side of constraint I leaves the current basis optimal. If you're not optimal anymore in that point, then that change is obsolete and should be ignored or not attempted at all. What is the importance of a sensitivity analysis? Well, there's a couple of reasons why a lot of businesses use sensitivity analysis. So the value of linear programming parameters could change. That's how business, that's how life. The parameters will change either in the objective function or in the constraints. So the price in the example of soldiers and trains, they are sold or available, availability of carpentry and finishing hours, that could be changing. If the parameter change, then sensitivity analysis will make it unnecessary to solve the problem again. So you're trying to do some kind of tweaks for your solution to adapt the new change. So in that case, if the profit contribution of a soldier increased to $3.5, then we would not have to solve the problem again, because the current solution remains optimal. So you're still good, you're still having profit, even the price increased. So knowledge of sensitivity analysis often enables the analyst or the data analysis scientist to determine from the original solution how the changes in the linear programming problem can change in its optimal solution, and do his judgment and decision based on that.